Here we go. So guys, today what we are going to do is we are actually going to go back to early September. And we are going to talk about a word. Actually, it's the last word on the screen. We're going to talk about a word that we mentioned in September and then never came back to. We assumed that you understood what bonding meant. We talked about what bonds do. And then, guys, we just skipped right through this and we haven't talked about it since. So what I want to do is I want to go backwards to September and sort of refresh your memory about when this idea of bonding first came up. Then, guys, what we're going to do today is we're going to do something rather repetitious. So the day is going to begin by talking about some terminology. You're going to draw a picture and label it. It's going to take like 3 minutes. Then, guys, after that, we are going to establish we're going to rely on what we know about trends on the periodic table, and we're going to figure out how these atoms interact when they bond based upon the way they behave. Remember, we understand that the metals are big and fat and weak. We understand that the nonmetals are small and strong, and we're going to leverage those understandings to figure out how they bond together. But guys, in order to do this, we are going to start, gosh, do you remember this? Guys, we are going to start there. Remember that? Yeah, I know, right? So, guys, good night. Doesn't that seem like an age ago? And we talked about hetero and homogeneous and physical and chemical properties and phases and interfaces and solutions and substances and oh my goodness. Well, guys, what does all that have to do with today? Well, guys, if you think about it, for the last month and a half, we've been talking about atoms. We've been talking about elements. We've talked about the nucleus. We've talked about how the nucleus changes, fission, fusion, radioactive decay. Then, guys, we started talking about the electron. By the way, I've graded your extra credit. Guys, we started talking about the electrons in atoms. And, guys, we've been talking about this forever and ever. Then what we did is we took all of these ideas about elements and looked at the periodic table and then talked about trends on the periodic table and how these elements are sort of the same and different from each other. Well, guys, now what we're going to do is we're going to take this leap and we're going to go from elements to compounds. And then, guys, this is where this all ties together, because we said that compounds are two or more elements bonded together. And I underlined it, and I bolded it, and I pretended like you knew what that meant, and I just kept going. Well, guys, that's what we're going to do today. We're going to talk about this whole idea of bonding, how it works, and what compounds get formed as a result. So, guys, this is the overview for the day. As we talk about compounds, you're going to find out that there are 3 types. One of the types of compounds are called salts. Now, guys, here's the thing you got to understand, and I doubt if you do. Guys, you understand that you can go to the grocery store and you can buy salt, and that's salt. But, guys, you got to understand that there are thousands of different salts. NaCl, sodium chloride, table salt, is one salt. But guys, there are thousands of salts. We just generically call this salt because it's the only one that we really eat a lot of. But guys, understand that in the world of a chemist, that is a salt, but not the only salt. And we're going to talk more. Then, guys, we're going to talk about another type of compound, which are called molecules. Salts and molecules are not the same thing. Then, guys, the third type of compound that we're going to talk about are what are called metallic compounds, and that's how we're going to wrap up the day. You get the idea? Okay, so what are we going to do first? We are going to talk terminology. So here's what you got to do. Draw yourself Mickey Mouse taking a nap. So, guys, make the big circle about 6 or 7 centimeters across, like 2.5 inches. And then make your small circles about 2 to 3 centimeters across, about 1 inch. Then, guys, you'll notice that in the middle of each one of these circles, we've got the nucleus. Draw that in. These are atoms, right? Yeah. Some of you may even know what molecule this is. Do you know? It's water. Guys, the big guy is oxygen. The little guys are hydrogen. This is a water molecule. All right, you guys all got your pictures? Okay, now what? So guys, I'm going to do my best to make this. I'll point with my laser, but some things are going to come in that are kind of subtle. This isn't. The first thing you're going to do is you're going to connect the nuclei with lines. And guys, notice that these lines extend through the nuclei and out both sides. So let's label those lines. Guys, those lines are what are called, in the plural, bond axes. Or in the singular, this is a bond axis. So we drew two bond axes. We labeled one bond, yeah, you get the idea, axis. Okay, so guys, if this is a bond axis, notice the idea is that they connect the nuclei. Then guys, if you look really closely, we're going to draw in a section of the bond axis. Well, actually, no, we'll do this one first. We're going to draw in this arc, then we'll do the section. Well, can you tell I actually drew it, though? Yeah, because I couldn't get my software to actually draw the correct arc, so I had to do it by hand. But guys, you guys understand from doing what little geometry we still teach you that that arc represents what? An angle, and it's actually called the bond angle. Interestingly, you're going to be learning the bond angles for all of these molecules, and you're going to find out that water has a 104.5 degree angle. Then guys, after that, this is the segment that I was trying to talk about. This guy right here, can you see it there? But notice guys, what we've got is the distance from the nucleus to the valence electron shell, and you already know the name of that. It's the radius. Good, Jer. And I'm glad that you said atomic, because guys, this is actually no longer the atomic radius. The atomic radius is the size of an atom when it's all by itself. This atom is involved in a bond, so instead of the atomic radius, it's what's called the covalent radius. That information is also on your periodic table. Okay, so now that we've got the covalent radius, guys, now watch up here. On this other bond axis, draw in a line or darken this so that it connects the nuclei. Okay, so guys, that distance also has a name. The name of that is what is called the bond length. And guys, one of the things that you've got to be able to do today is calculate bond lengths for molecules, given the data on your periodic table, but I'm guessing you all see it. If you want to know how long this line is, what could you add up? The two covalent radii, right? If this is the well, here, let me do it this way. If this is the covalent radii for oxygen, and if that's the covalent radii for hydrogen, add them up and you get the bond length. Does that make sense? So guys, the equation actually looks like this. So bond length is equal to sigma covalent radii. But you guys already know what sigma means because we talked about it when we calculated average atomic masses. What is sigma? What does it mean? Add them up. Sum, sigma, sum, SUM, add them up. So all you're going to do is add up the covalent radii. So to figure out that bond length, the distance between the nuclei, look up the covalent radii for oxygen, look up hydrogen, add them together. Does that sit okay for you? All right. So guys, now this is going to become redundant. What we're going to do now is we are going to talk about salts, molecules, and metallic compounds. And the way that we're going to do this is we're going to talk about the atom pairings that form each one of these compounds. Atoms bond together to make compounds, and we're going to talk about the ways that that happens to form salts, molecules, and then metallic compounds. So can I get rid of this? Okay, guys, do not write down anything on this slide, please. This is all just conversational, transitional stuff. So, guys, here's what we know. We know that chemical bonds are attractive forces that hold atoms together. Does that make sense? Okay, so when atoms bond together, the atoms actually come together and they attract each other. Now, guys, here's the question. And maybe you know this, maybe you don't. Let's see. Guys, when atoms bond together, what part of the atoms are actually coming together to form the bond? Good, the electrons. So guys, when these attractive forces are created, they're actually created in the valence electrons. As the valence electrons interact with each other, that creates the attractive forces. Now guys, when this happens, it can happen in lots of different, well, not lots, it can happen in 3 different ways. And so the different type of bonds that form depend upon the characteristic properties of the atoms that are bonding. So guys, let's talk about it. What's over here, the metals or the non-metals? These are the metals. Are they big or small? Big, weak or strong? Weak. So what do they do with electrons? Give them away. Over here are the non-metals. They are small and strong. So what do they do with electrons? Take them in, right? So guys, that determines the type of bond that forms. So if you have a metal bonding with a metal, that'll form one type of bond. If you have a non-metal with a non-metal, that'll form a different type of bond. And then a metal with a non-metal forms an even different type of bond. So guys, that's the way we're going to understand this. When a metal bonds with a non-metal, what does that do? When a non-metal bonds with a non-metal, what does that do? And when a metal bonds with a metal, what does that do? And guys, you're going to find out that the answers are salts, molecules, and metallic compounds. See where we're going with this today? Do you understand the big picture? Okay, let's dig in. Guys, do not write this down, but be ready to take notes. So let's review. What are the chemical properties of metals? Where are they on the periodic table? Over on the left, are they big or small? Big, weak or strong? Weak. So what do they do with electrons? Give them away. So guys, what are the properties of non-metals? They're over on the right, big or small? Small, stronger, bigger, strong or weak? Weak or strong? Strong. So what do they do with electrons? Take them in. Now guys, picture this. What do you think is going to happen when they get together? When a metal, which is big and fat and weak, gets together with a non-metal that's small and strong, what's going to happen? What's the non-metal going to do to the metal? Kick its trash and steal its electron, right? Because non-metals are small and strong, metals are big and fat and weak, and this non-metal is going to grab a hold of that electron and rip it away. But then what happens? Well, guys, what happens to that non-metal if it gains an electron? If it gains an electron, it becomes negative. What happens to the metal if it loses an electron? It becomes positive. What do negatives and positives do? Attract. And guys, that makes salts. Does that sound familiar from the homework we graded last time? Remember what we did in homework. We looked at sodium, this was question 5. Sodium losing an electron, that's a metal. Chlorine gaining an electron, that's a non-metal. And at the very top of the second page of your homework, we said the sodium's positive, the chlorine's negative. They attract each other. So guys, let's bring that all together. Ready? You need to write this down with me now. So guys, a metal with a non-metal, start there. We're just going to summarize what we just said. So when a metal bonds with a non-metal, the metal is big and fat and weak, the non-metal is small and strong, the non-metal steals from the metal, that forms an ionic bond. So how does ionic bond formation go? This is all review from what we just said. So a strong nonmetal steals electrons from a weak metal. And guys, think about that. Make sure that makes sense up inside your brain. The nonmetals are small, so they're strong. The metals are big, so they're weak. And the nonmetal steals from the metal. Now guys, but that's not where the story ends, because when this happens, what happens to the charge of the nonmetal? It becomes negative because it stole an electron. The metal becomes positive because it lost an electron. So ions are formed by this process. And then guys, as we've said, what do these ions do? They attract each other, and when they do, when they attract one another, they bond together and they form what are called salts. Guys, that's all a salt is a positive metallic ion and a negative non-metal ion attracting each other and sticking together. And guys, any possible combination can do this. lithium with fluorine, potassium with bromine, strontium with oxygen, beryllium with sulfur. Doesn't matter. If you've got a metal and a non-metal, the non-metal will steal electrons, they'll attract together and form a salt. Yeah. Ugh, that's the thing that's interesting. Tell me what you're thinking. Good. So hydrogen is a metal, right? And oxygen is a non-metal. And by what we just said, that should be a salt, right? Hydrogen, did you guys hear that? Because it's a really good insight. By what we just said, that means water should be a salt, and it's not. So what's going on? Hydrogen is actually a freakishly strong metal. If you look at the electronegativity of hydrogen, it's like 2.2, and then lithium is like in the decimal places. You see what I'm saying? So the electronegativity of hydrogen is 2.2, and then lithium drops all the way down below 1. Do you see where I'm looking? So what's going on? Well, the trick is hydrogen is such a small atom and it doesn't have any inner core electrons, so there's no shielding. So hydrogen is the one exception to what we just said. Hydrogen cannot form ionic bonds. The reason is because hydrogen is, even though it's a metal, hydrogen is so strong that nobody can steal from it. So hydrogen always forms covalent bonds even though it's a metal, and it's because it's freakishly strong. Go ahead, Abby. Because it's a gas. Yeah, hydrogen is a gas even though it's a metal. So hydrogen is a metallic gas. And we're going to talk about why it's a gas at the beginning of the next unit. It's fascinating. Yeah, it's really cool. So you guys good on this idea of salts? Metal, non-metal, metal steals, non-metal loses, ions, boom, salt. Good? Okay. Check this out. So guys, this then is what this looks like. So if you didn't understand this, salts are compounds that contain ionic bonds. You good? I'll let you write it down if you want. This took forever. Did any of you print the notes? There are 19 slides in the notes today. These were really hard animations. Okay, so guys, here's what we know. We know that sodium bonds ionically with chlorine, right? We looked at that in the last homework assignment. I'm going to pick two different elements to show you another example of this. So guys, I'm going to look at lithium and fluorine. So this is the way this goes down. You ready? Here is a lithium atom. Good? 3 protons, 3 electrons. Here is a fluorine atom. It's got 9 electrons, 2 here, 7 there. So guys, how many electrons is lithium going to give away? 1. How many electrons can fluorine take in? Convenient, right? It's 1. So guys, here's what happens. When lithium and fluorine come together, who's stronger? The small fluorine or the big lithium? Small fluorine, right? So fluorine reaches out to lithium, boom, 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 and steals its electron. Now, when that happens, what happens to the charge of lithium? It becomes positive. What happens to the charge of fluorine? It becomes negative. What do positives and negatives do? They attract one another, and this forms an ionic bond, and this is now a salt. And the name of this salt is actually lithium fluoride. You get the idea? That's ionic bonding. Questions about ionic bonding? You guys good? All right. So now, guys, we're going to play the same game. This is going to become a little tedious, but that's fine. So here's the question. Going back to the periodic table, guys, what are the chemical properties for the nonmetals? Just the nonmetals. Are the nonmetals big or small? Small. So are they weak or strong? Strong. So what do they want to do with electrons? Take them in. So now, guys, this question. Picture this, because I think you can figure it out. What will happen when 2 small, strong nonmetals get together? One pulls and the other pulls but they're both strong, so who's going to win? Neither one of them. Guys, have any of you ever worked at the nursery at church? You've seen this happen, right? There's that greedy kid, like a 2-year-old in nursery, right? And the first word that he learned was not mom or dad, it was mine, right? And this kid just walks around and it's mine, 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 just stealing, just stealing. This kid is a non-metal, right? He's a stealer, and it's mine, mine, mine. And then eventually this kid makes the mistake of trying to steal a toy from a kid that is equally as greedy and strong. Right? You've seen this happen. And the mine. And that kid goes, it's mine. And they're both going, mine, mine. And neither one of them wins. But neither one of them loses, and they both get locked onto the toy. And they're both so stinking stubborn that neither one of them will let go, and they are literally bonded together. Guys, atoms do exactly the same thing. It's mine, 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 and neither one of them is stronger than the other, and they end up sharing those. You can think, actually, it's a weird way to think of sharing, that sharing is actually the result of greed and equal strength. But guys, really that's what's happening is these electrons, the atoms both lock onto these electrons, neither one wins, they share and they're bonded together, just like two kids in the nursery. Now guys, this has a name, so let's start getting this down. So this can happen, and don't write this down, but guys, this can happen in one of two possible ways. If these two atoms have perfectly the same strength, the sharing will be equal. But the sharing can also be unequal. If one of the kids is slightly stronger than the other, there's going to be some unequal sharing that takes place, and we're going to look at both. So this is what you need in your notes. Non-metal, non-metal. Write that down. So non-metal with a non-metal. So guys, what happens when two non-metals get together? It's the mine, 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 right? Neither one wins, neither one loses. They end up locked together, which we describe as sharing. And the name of this is what is called non-polar covalent bonding. So guys, when we say covalent, you may up here want to write down the word sharing. Covalent, valent, valence electrons, co meaning to share, like cooperate. So guys, when we talk about nonpolar covalent bonding, the word covalent means sharing valence electrons. So how does this work? Well guys, nonpolar covalent bonding goes like this. If you have two atoms of the same nonmetal, it turns out if they're the same nonmetal, the same atom, like two fluorines, two oxygens, two nitrogens, two bromines, two chlorines, guys, if they're the same element, they have the same strength, right? And if they have the same strength, they will share perfectly equally. And this forms what are called nonpolar molecules. So guys, let me show you what this looks like. Y'all caught up? Can I show you my pictures? Is that okay? You're good? Okay. So guys, I chose, again, the element fluorine because we're kind of accustomed to fluorine. So guys, here's fluorine with 7 valence electrons, and now we've got two of the same nonmetal. So who's stronger, the fluorine on the left or the fluorine on the right? They're the same. But both of these are the bullies in the nursery, right? Mine, 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 mine. They're small and strong. So what happens? Well, guys, what happens is this fluorine reaches out and tries to steal that fluorine's electron, right? But then this fluorine reaches out and tries to steal this fluorine's electron. They're fighting over the toy. But guys, neither one of them wins. So this one partially steals his electron, this one partially steals his electron, and these electrons end up pairing up in between. But now, guys, what happens is these atoms are attracted to that pair of electrons. But notice, because they have equal strengths, this pair of electrons ends up right in the middle, and we call that equal sharing or nonpolar covalent bonding, which forms nonpolar molecules. This would be what is called a nonpolar F2 molecule. You get the idea? Okay, but guys, understand that this only happens in rarer instances, right? In order for the bonding to be nonpolar, what has to be true of the two atoms? It's got to be the same atom, and that doesn't happen very much. So what about all the other examples? Nitrogen with oxygen, nitrogen with sulfur, fluorine with chlorine, silicon with... What about all the examples where two different nonmetals are bonding together? Well then, guys, what happens is we end up with unequal sharing. So this is the other type of covalent bonding. Scratch this in your notes as well. This is what is called polar covalent bonding. So how does polar covalent bonding work? Well, guys, polar covalent bonding happens when we have different nonmetals that are close enough in strength that they have to share. But they're different enough that they don't share equally. And I'll show you pictures in a minute. But guys, it goes like this. When these different nonmetals come together, this sharing is unequal, and it creates something called dipoles. Now guys, as you're writing down the word dipoles, let me talk to you about this. I'm introducing the idea of dipoles to you right now. I'm going to show you what they are, but guys, this will not be on the test. We will not test you over the concept of dipoles. I want to introduce it right now, and then guys, it's going to be a major topic in the next unit. So don't get all caught up with dipoles right now. Just understand what we're saying is the sharing is unequal, and I'll show you what that means in a minute. But let me define dipole for you right now. Guys, a dipole is the partial charge on a bond caused by unequal sharing. Just write it down. Because what I'm going to do is when we start the next unit, I'm going to call your attention back to this. Just to say, hey, we already talked about this. It's not unfamiliar. So basically, this page in the notes is going to come back up in early December when we start talking about polar covalent bonding in greater depth. Okay. So guys, when this happens, this unequal sharing, we form what are called polar molecules. Do you guys believe we're almost done? But I saved my best animation for last. It's almost better than the electronegativity animation. You remember how good that one was. Okay. All right, you guys ready? Polar covalent bonding. So now we're going to grab two nonmetals. Remember, they're small and strong. Two nonmetals, but they're going to be different nonmetals. So I chose oxygen, and then I chose to stick with fluorine just because it's kind of a familiar place to be. So guys, now we're going to talk about what happens when oxygen and fluorine bond together. Now, guys, which element will be smaller, the oxygen or the fluorine? Let's do that. Guys, make sure you get this. Madeline, make sure you see this. Which is smaller, oxygen or fluorine? Guys, you got to know the trends. As we go to the right, they get smaller. So fluorine will be smaller. So if fluorine is smaller, will it be weaker or stronger? Strong, good. Okay, now let's talk. So guys, here's the way this goes down. So fluorine and oxygen, fluorine is a little bit smaller, so fluorine's a little bit stronger. So here's how it goes. Fluorine reaches out to the oxygen and it tries to steal its electron. Then oxygen reaches out to fluorine and tries to steal its electron. But guys, look at where the electrons ended up. They aren't right in the middle. Why not? Because fluorine's a little bit stronger. So it's kind of like two kids fighting over a toy, and this kid is a little bit stronger, so the one kid is sort of reaching out a little bit, and the other kid's kind of got it close to his chest. So it's like, I'm stronger, so it's going to be closer to the fluorine because the fluorine's stronger. So now when these atoms are attracted to these electrons are going to end up close to the fluorine and further away from the oxygen. And guys, this is what creates dipoles. So the electrons are negative, so that means this end will be slightly negative. We call it dipole negative. Don't worry about it if it doesn't make sense. This end, because the electrons are over here, this end will be slightly positive, and we call that the positive dipole. Guys, we're going to talk about this a ton more in the next unit. I wanted to introduce it to you now. You guys okay? Can I go on? All right, here we go, guys. One more to go, so let's think about it. The first thing we talked about was metal, non-metal. What kind of compound did that create? Salts. Then we talked about non-metal, and what did that create? Molecules, either polar or non-polar, depending upon the combinations. So now, guys, we need to talk about metal with a metal. This gets messy, literally. You ready? Talk to me about metals. Chemical properties of metals, big or small? Big, weak or strong? Weak. So guys, what do metals want to do with electrons? Give them away. So guys, what do you think is going to happen when a bunch of metal atoms get together? Exactly. Here, take my electrons. No, I don't want them. You take them. It's literally like hot potato. Nobody wants the electrons. Everybody's giving them away. Nobody takes them in. So where do the electrons end up? All over the floor, so to speak. Guys, nobody wants the electrons. We don't have any non-metals in the picture, so nobody can take them in. They're all just giving them away, and they all just end up running wild throughout the substance. So guys, let's talk about the type of compounds that form. So here's how this goes. Here's a bunch of lithium atoms, right? Go ahead. Bingo! That's why metals conduct, because guys, what is electricity? Electrons. That's why metals conduct. They're going, I don't want them, I don't want them, I don't want them, and you hook them up to a battery and the current just goes, no one wants it anyway, it just flows right through. Good for you, Maddie. Exactly. All right, so guys, here we've got a bunch of lithium atoms, right? They're big and they're fat and they're, check this out. They're big and they're fat and they're weak, and what are they all doing with their electrons? Ready? Ready? Giving them away. Oh, baby. Huh? That took forever. But guys, literally, they're all just giving them away. But now check this out. If all of these atoms gave away electrons, what? Please don't. Oh, it's a fly. I thought it was a bee. Okay, so guys, if all of these atoms gave away electrons, what does the charge of the atoms become? They all become they all become positively charged. But guys, what then is the charge of this mess in here? That whole mess is, oh baby, negative. So guys, literally what we end up with, inside of metals is we've got all these positively charged atoms floating around in a soup of electrons. And so what happens is all of these positives are just attracted to this sea of electrons. And as Maddie said, that's why metals conduct electricity. If this were a wire, or this, because this conducts electricity, you put a current in here, it just flows through the sea and comes out the other side. But guys, think of what else you know about metals. Do you remember when we said metals are ductile? Okay, so let's talk bendable. That's malleable. Guys, why are metals bendable? Because all you're doing is smearing the sea, right? The sea doesn't care if it's going this way or this way, it's still the sea. Now guys, why, when you draw out a metal, is it ductile? Does it turn into a thin wire? All you're doing is stretching the sea, right? Why are metals shiny? Because literally it's like have you ever done this? You've been up in the mountains still morning and the lake is completely flat and it works like a mirror and you can see the reflection of the mountains. Same thing here. Guys, that's why metals are shiny. It's because this sea is actually perfectly flat on the surface and light bounces right off of it and makes them shiny and reflective. Guys, everything that we know to be true about metals is true because of this. And it has a name, and you need to write it down. Guys, this is what is called the sea of electrons. So when you think about metallic bonding, you need to think about what is called the sea of electrons. That's actually what they call it. That's how you're going to learn it in college. They talk about the sea of electrons. And guys, I actually lifted this image out of my AP book. This is the way we think about metals. But I think mine is way cooler because it actually looked like a sea. I should have a textbook. All right, you guys good? Okay, so guys, we're done. Except for, and this is up to you, there's been a lot of information shared. And guys, I function best if I've got somewhere that I can go and sort of see the big picture. So I offer you this as the big picture. If you want to write this down, awesome. If you choose not to, there really isn't anything new in these notes. But what I've done is I created a table that summarizes everything we just went over. If you want to write this down, make each one of these horizontal rows 3 lines tall, and then make this thing as wide as your paper, and make each one of these columns 1/4 of the width. If you choose not to do this, that's fine. If you want to get really efficient about this and just go home and print the notes, it's right there in the class notes posted on our website. But guys, if you are going to take the time to write it down, I'll give you a couple minutes to scratch down these boxes. And then guys, label them. It goes like this. Across the top, we're going to go type of bond. That's obviously ionic, covalent, and and metallic. Hold on, I went one click too far. So guys, we've got type of bond, ionic, covalent, and metallic. And then moving left to right, we're going to talk about what atom pairs form these relative to metals and nonmetals. Then how do they form, and then what are the properties of the compounds that form them? Again, guys, this is a summary. But if you want the summary, I'll wait for you to write it down. You guys may get out of here without having homework. I was about to say you won't have homework for the weekend, because today really feels like the weekend should be closer. But Isabel and I had a very happy thought this morning before class started. A week from today, you will not be here. It's Thanksgiving break. But on a sobering note, 10.5 hours from right now, I'll still be here. Well, that's because you're wrong. Little bit of parent-teacher conferences. You guys ready to fill this thing in? No. Hurry, Jeremy. Faster. So like the wind, so very old one. What movie is that from?
Three Amigos.
All right, you've redeemed yourself. Can I tell you my sad Three Amigos story? It is, if you haven't seen Three Amigos, it is quite possibly the best movie ever, with the possible exception of Better Off Dead.
What about
Princess Bride's way overdone. It's a great movie, but guys, so Three Amigos, right? It actually came out when I was in high school. I went to see it in the theaters. The opening scene of the Three Amigos, where all three of them are on their horses and they're singing the Three Amigos song, and they hold out that note for like 1.5 minutes. I got up and walked out of the theater. I'm like, you have got to be kidding me. I'm leaving. I've never left a movie. I got up and left. And then it turned out to be my favorite movie in the whole world. All right. You guys ready to go? Okay, so guys, you should be able to fill this out. So if you are doing this, let's also use this as a check for understanding. So guys, when an ionic bond forms, what are the element pairings that form stealing bonds? A nonmetal with a metal. The metal is big and fat and weak. The nonmetal is small and strong. The nonmetal steals from the metal. So how then does this bond form? What does the metal do to the nonmetal? Steals an electron. What does that form? Ions. What do those ions do? Attract. So guys, we say that this way. Electron transfer that creates ions which attract. That is an amazingly good summary of how this works. And then guys, this forms salts. I gave you a couple examples, sodium iodide, calcium chloride, sodium iodide. We looked at sodium fluoride, I believe. No, lithium fluoride. We looked at in the animations. And then guys, this may actually be a little new. You can lift it out of the notes if you're not doing this. There are actually some things that you need to know about salts. So if you're not writing down the whole table, you should at least write down the idea that salts are ionic in all phases, but interestingly, their solids don't conduct. But their solids are really hard to melt. These ionically bonded substances have ridiculously high melting points. If you don't believe me, go home tonight, grab a saucepan, fill it up with table salt, put it on the stove, and try to get it to melt. You can't. You cannot create temperatures high enough in your kitchen to get salt to melt. Oh yeah, we'll Google it as soon as we're done. Yeah. Okay, you guys caught up with me on salts? Okay, so now guys, covalently bonded substances. Again, you should know this. What element pairs form covalent bonds? Two nonmetals. If they're the same nonmetal, it's nonpolar. If they are different nonmetals, it's polar. Then how do these bonds form? Well, they form through sharing. And they form molecules like carbon dioxide and water. Because also, all of the biologic molecules that you learned about, whether it's sugars or fats or proteins or DNA or RNA or enzymes or any of that stuff, all of those things are covalently bonded, with very few exceptions. So what do you need to know about molecules? Well, they don't contain ions, they have low melting points, and none of them conduct electricity. How low is the melting point of molecules? Water is already melted. But you could try sugar. You guys know you can melt sugar in a kitchen. Caramel, right. You've done it. If you haven't, you should. Okay, then guys, finally metallic bonding. Metallic bonding is obviously formed by metals. This is the delocalized sea of electrons around weak nuclei. What do we call that? Sea of electrons. And guys, you need to know these things, but you already know it. Metals conduct, they're ductile, they're malleable, they're shiny, they have high melting points. You already knew that. So, guys, we are done. You already have your homework in your possession. It is assignment number 2. We will grade this on Friday. And then, guys, for the rest of this unit, we are only going to talk about molecules. And we are actually going to look at how atoms bond together to form molecules. And then we're going to break out the model kits and we're going to start building molecules. But that's not going to be until after Thanksgiving. What's going to happen is this. Friday, you're going to learn to represent the structures of molecules. Tuesday, the day before Thanksgiving, you're not going to learn anything new. We're going to spend a second day on that. Then after Thanksgiving, we're going to start playing with the model kits. So guys, if you're going to miss school on Tuesday, is it Tuesday? Yeah, Tuesday. If you're going to miss school on Tuesday, it's a wonderful day to miss. You're not missing any instruction. You are missing a second day of reinforcing what you learned on Friday. And you've already got the homework in your possession. So guys, we've got, holy smokes. Guys, we got 20 minutes.